Hello, everybody. We are going to cover chapter 14 today. Chapter 14 is talking about simple linear regression. Simple linear regression. Before we get started with chapter 14, I need to refresh your memories about working with two variables. Back in chapter 2 and chapter 3, when we were working with two variables, we were concerned with three things, if you remember. If there is a relationship between two variables X and Y. Number one, if there is a relationship between two variables. Number two, if the relationship is positive or negative. Number three, how strong is the relationship? We're going to be dealing with those in chapter 14. And also, we're going to find out another factor called coefficient of determination. Coefficient of determination, which is new, and we're going to learn this in chapter 14. As the name says, determines what percentage of the actual value of Y variable can be determined by given value of X. Or another way of saying this, for any given value of X variable, what percentage of the actual value of Y variable could be determined? And that is called coefficient of determination. Now consider the two variables of X and Y, if you guys remember. One being the amount of money that you spend promoting your business, that's X. And the other one being the amount of sales, and that is Y. So for the amount of X that you spend promoting your business, what kind of change are you going to see in the amount of sales? Those are the two variables. And if you guys remember, if there is a positive relationship, if we want to draw the line to show positive relationship, the trend line, the scatter diagram and trend line, this is positive relationship. And if there is a negative relationship, and if there is no relationship, we have the horizontal line. If you guys remember this from chapter 2 and chapter 3. All right. Now, in chapter 14, we are going to work with a linear equation to help us finding the estimated value of Y when we have the value of X. Those of you remember the linear equation? Y is equal to mx plus b. This is the linear equation. y is equal to mx plus b. If you guys remember, m is the slope, x is the x variable, b is the y-intercept. So for any given value of x, we should be able to tell what the estimated value of y would be. If this is the amount of sales, and this is the amount of money that you spent promoting your business, this is the y-intercept, and this is the slope. We actually are going to find or develop, rather, the linear equation for the two variables that we are dealing with. Once we develop the linear equation, then we can go ahead and use any value for the x in order to find what the estimated value of y would be. Now, starting chapter 14 with this little introduction, there are three linear equations that we're going to deal with. Well, as a matter of fact, we're going to only use one of them. We're going to utilize just one of these linear equations. There are three that I'm going to list for you guys. Before we go any further, this page see if I can make it to focus. This is my formula sheet, my cheat sheet. I have already taken a picture of it, and I have loaded up on a beachboard that I would suggest you guys to download it and print it out when you are working on problems. Have this formula sheet handy, and this is going to help you a lot by saving time and being efficient when you are going to utilize these formulas. The reason I have collected all the formulas that we need to use for this part of chapter 14, because we're not going to cover the entire chapter 14. And these formulas on this sheet, these are the formulas that you need. And once you have it all together, it's going to make it a lot easier and more efficient when you're going to utilize them using and solving the problems. Now, the first form of the simple regression formula, which is called model formula. So model formula is y equal beta sub 0 plus beta 1 times x plus epsilon. All right? This is the model formula, meaning if we were living in a perfect world, that we wouldn't make a mistake when we are doing the sampling, that we do not involve our biasness when we select our samples, we would be able to have the exact value of beta sub 0 is the y-intercept, beta 1 is the slope, x is your x variable, epsilon is the residual error or error term. Error term or residual error. That means in a perfect world, we'd be able to even calculate the amount or the value of the difference between the actual value and the samples, the entire population and the samples. The difference between the actual value of y and estimated value of y, that is known as error term or residual error. Okay? We're not going to use this formula, but you guys have to be familiar with it. It's in the book. The second formula, which is called expected value of y formula, is E of y equal beta sub 0 plus beta 1 times x. So if you look right here, there's no epsilon in here because we are not capable of actually calculating the error term. We're not going to use this formula either. Why do we have to learn about it? Because it's in the book. The actual formula that we're going to use is called estimated value of y formula. And that is y hat equal b sub 0 plus b1 times x. So this is the formula that we're going to use. We're going to be working with for linear equation of the two variables. This is called y hat. Y hat is the estimated value of y, B sub 0 is the y-intercept, B1 is the slope, and x is x variable. Now, the whole idea at the end you're going to see of covering this chapter is for us to be able to test. There's a test called t-test. To test for B1. Why? Because B1 is the slope. If B1 is 0, that means there's no slope. That means there's no relationship between the two. And if there is a value for B1 which is positive, then there is a positive relationship between. Positive relationship means for any increment or decrement in one variable, you will see the same thing in the other variable. Example, if the value of x is increasing, so does the value of y. If the value of y decreasing, so does the value of x. This is called positive relationship. The negative relationship is when B1 comes out to be negative, and also when one variable is increasing, the other one decreasing, and vice versa. So when we are dealing with two variables, the first thing that we have to do, we have to develop the line regression equation. This is the estimated value of y or line regression equation. Let's just use two sets of variables, two values sets of values for these variables. Oh, by the way, the x variable is called independent variable, and y variable is called dependent variable. The reason, the value of y is going to be calculated based on given value of x. In other words, the value of y is depending on whatever the value of x is. That's why that the x variable is called independent variable, and y variable is called dependent variable. So let's say that we have x and y. Let's say that x is 1, 3, and 4, and y is, well, we make it more easier for calculation. I don't use calculator, so 1, 3, and 5, and then we have 4, 6, and 5, and let's see, 4, 6, and 5. Okay? We want to go ahead and develop the line regression equation for these two variables. You can tell by looking at the values. X is 1, y is 4, x is going up, it's going up, it stays the same. I mean, going up, that stays, this is going down. So there is a slightly a positive relationship between the two. Now let's just go ahead and see what the value of b sub 0 and b1 would be, and how do we calculate those values and plug them into this equation. So to develop this equation, first we have to find these two. So b1 is equal to sigma of xi minus x bar times yi minus y bar divided by sigma of xi minus x bar squared. This is how we find b1. So x bar in here is going to be equal to 3, and y bar is equal to 5. xi minus x bar, so xi minus x bar, xi we have 1, 3, and 5, minus 3, minus 3, minus 3, this is negative 2. This is 0, this is 2. Okay? And then yi minus y bar, 4, 6, and 5, minus 5, minus 5, minus 5. This is negative 1, this is 1, and this is 0. Now we go ahead and multiply these. So xi minus x bar times yi minus y bar. That means we multiply these by these. Okay? So we're going to have xi minus x bar times yi minus y bar. Negative 2 times negative 1, that's 2. 0 times this is equal to 0. 0 times this is equal to 0. And then we apply the sigma. So the value for top is going to be equal to 2. So in this case, we have 2 divided by 1, 2, 3. 1, 2, 3, that's 3. I'm sorry. Divided by xi minus x bar squared. So we do, this is xi minus x bar, xi minus x bar. Now we do a square. So negative 2 square is positive 4. 0, positive 2, that's 4. Sigma, that's equal to 8. So 2 divided by 8. So our B1 comes out to be, B1 is equal to 0.25. This is our B1. Okay? So I'm going to go ahead and erase these, and I'm going to have my B1 equal to 0.25, 0.25, and then finding B0. B0 is equal to y bar minus B1 times x bar. Y bar is 5 minus B1 is 0.25 times x bar is 3. So B sub 0 is equal to negative, positive, that's negative, negative 1.25. 1.25. Sorry, I made a mistake. 5 minus 3 times 0.25, that is 0.75. Okay, and then this is 4.25. So our B0 is 4.25. I didn't see that. So 4.25 is our B0. Our B1 is 0.25. So our line regression equation would be B sub 0, 4.25 plus 0.25 times x. So this is our line regression equation. Now, for any given value of x, you'll be able to tell what the estimated value of y would be. Let's go ahead and give the value of x1. X is equal to 1. 1 times 0.25, that's 0.25. 4.25 plus 0.25. So for x equal to 1, y would be 4.25 plus 0.25. So estimated value of y would be 4.5. And here we have 4. This is estimated value. Close enough. Now let's say that x is equal to 3. If x is equal to 3, 3 times 0.25, that's 0.75. Plus 4.25, that's 5. So when x is equal to 3, the actual value of y is 6, but we come up with estimated value of y being equal to 5, which is close enough. Now let's see, when x is equal to 5, 5 times 0.25, that's 1.25. Plus this, that's going to be equal to 6. Or you can use a different value. You can say if x is equal to 10, then what is the estimated value of y? The estimated value of y would be 2.5, 2.75 plus 4, that's 10 times 0.25, 2.5, 6.75. 6.75. If x is equal to 10. All right? So this is a very important part whenever we are dealing with two variables that we're going to find out how strong the relationship is and for what value of x, or for any value of x, what percentage of value of y can be determined. That's called coefficient of determination. On the PowerPoint slides, if you guys go to slide, let's see. Slide number 13, there is an example right there that they are doing the same thing that I did right here for you. We're going to solve a problem as well. Now let's go ahead and start solving a problem out of the book, or two problems, problems 1 and 4. One and 4. For 11th edition users, problem number 1 on page 569. For 12th edition users on page 607. And those of you with 13th edition, 609. 1, 2, 3, 4, 5. So here is, well, I don't have to write down the value. Well, I'm going to do that anyway. So I have these in here. One, 2, 3, 4, and 5. Then we have 3, 7, 5, 7, 5, 11, 14, 11 and 14. Part A, develop a scatter diagram for these data. So this is x, and this is y. 1, 2, 3, 4, and 5. Let's say 5, 10, and 15. This is 15, for example. When x is equal to 1, y is equal to 3. This is 1 point right there. When x is equal to 2, y is equal to 7. This is 2. 7 would be approximately right here. When x is equal to 3, y is equal to 5. This is right here. When x is equal to 3, y is equal to 11. 1, 2, 3, that's 11 right there. When x is equal to 5, that's equal to 14. This is 5, 14 approximately right here. So this shows a positive relationship. This is for part A of the problem. For part B, what does this kind of diagram show? What kind of relationship for part B? It shows positive relationship. For part B, it shows positive relationship. For part C, try to approximate the relationship between x and y by drawing a straight line through the data. So this is part C. Okay, this is for part C. For part C, the scatter diagram or the line, so many lines could be drawn to show the relationship between the two variables. The most important part of this problem is actually part D. Develop the estimated regression equation by computing the value of B0 and B1 using the equations 14.6, 14.7. 14.6, 14.7, those are the equations for finding B1 and B0. All right? I did go through those calculations of the xi minus x bar, yi minus y bar, and xi minus x bar squared in my first example with 3 variables. So in here, we just try to put in the values. First, we have to find x bar and y bar. So now we're going to go to part D. For part D, x bar, that's equal to 3, and y bar, I think it's equal to 8. If I am not, yeah, y bar is equal to 8. So that's, you add these, that's 40 divided by 5, and this is 15 divided by 3. 15 divided by 5, divided by 5, that gives us 3. So those are the two that we need to have. And then writing down the formula, B1 is equal to sigma of xi minus x bar times yi minus y bar divided by sigma of xi minus x bar squared. So I have the value of xi minus x bar in yi minus y bar. So xi minus x bar times yi minus y bar, that's equal to 26. The top value is 26. This one down here is 10. Again, if you want to do these, so xi minus x bar, those are xi 1, 2, 3, 4, 5, minus x bar, which is 3. And then you find that, and then you do yi minus y bar. Those are 3, 7, 5, 11, and 14, minus 8. You know what? Let's do this for this problem. I don't want to do it, but let's do it for this problem. Then we don't do it for the other problems. So now this is -2. This is -1. This is 0. This is 1. And this is 2. This is -5, -1, -3. This is 3, and this is 6. Now we multiply these two by one another. So xi minus x bar times yi minus y bar. -2 times -5, that's 10. -1, that's 1. 0 times -3, that's 0. 1 times 3 is equal to 3. 2 times 6 is equal to 12. Now we add them all up. 2, 3, 12, 15, 16 plus 10, that's 26. 26. Divided by xi minus x bar. Xi minus x bar, xi minus x bar square. This is, let me see if you guys can see this, or maybe if I, no. You know what, let me erase. Well, thank God this has been recorded. Let me just erase all these and just do xi minus x bar square. Okay? So we're going to do 5 minus 3, that's equal to 2. Now let's say xi minus x bar squared. -2 squared is 4. -1 is 1. 0, 1, 2 squared is 4. 4 plus 1 plus 1 plus 4, that's equal to 10. So 26 divided by 10, then our B1 comes out to be 2.6. So over B1 is going to be 2.6. Now do B sub 0 is equal to y bar minus B1 times x bar. Y bar is 8. B1 is 2.6 times x bar, which is 3. 3 times 2.6, 7.8. 8 minus 7.8, that would be 0.2. So this is the value for B0. B sub 0 is equal to 0.2. Therefore, our line regression equation would be y hat equal to 0.2 plus B1, which is 2.6 times x. This is our line regression equation. Look, for any given value of x, we're going to find out what the estimated value of y would be. Estimated value of y. Let's say that x is equal to 1. 2.6 plus 0.2, it's going to be 2.8. Y is equal to, the actual value is 0.3, is 3. Close enough. X equal to 2. 2 times 2.6, that is 5.2. Plus 0.2, that's 5.4. It's 7. So same for the rest of it. Just go ahead and substitute value for the x to find the estimated value of y. So that's for part B. For part E, use the estimated regression equation to predict the value of y when x is equal to 4. Now, when x is equal to 4, let's see what would it be. This is for part E. For part E, y hat is equal to 0.2 plus 2.6 times 4. 4 times 2.6 would be what? 10.4? Yeah, 10.4. 10.4 plus 0.2, that's 10.6. So here it says 11. Close enough. All right. Now, problem number 4. Now that this is, I just want to go ahead and plug in the values because the video you can always play back and go over the explanation. And frankly, I don't even think if I have to solve this because that's exact same concept. Well, let's just go ahead and do number 4 as well. For number 3. Number 3, I made a mistake. We have to do, why does it say number 4? Let me see if it's, no, that's a mistake. Number 4 is not the same. If you see on the slide, it says number 4, or maybe you guys have the corrected edition of the slide. If it says number 4, it's supposed to be number 3 because number 4 is not the same for all editions. For number 3, we have x 2691320. 26913 and 20. For y 718.9, 718.9, 26, and 23. And 23. Okay? I'm going to just go ahead and do part D of this problem as well, because part ABC is the same as the previous problem that we just did. In part B, wait a minute, use estimated. No, part A, I'm not going to do part A because that's the same as what we did in previous problem. Part B says develop the estimated regression equation for these data. So B1 is going to be equal to the sigma of xi minus x bar times yi minus y bar divided by sigma of xi minus x bar square. So B1 is equal to 110 divided by 20. 110 divided by 20. X bar is equal to 65, y bar is 117. This is 65 and y bar is 117. So B1 comes out to be 5.5. And B0 is equal to y bar, which is 117, minus B1, which is 5.5, times x bar, which is 65. So B0 comes out to be negative 240 point, let's see, B0 is negative 240.5. 240.5. Wait a minute, no, I'm making a mistake. No, I'm making a mistake. This is the wrong problem. 15, let me see. Problem number 3. Yeah, this was, hold on guys. B x bar is equal to, x bar is, sorry guys, I was reading off of 8 different notes. So x bar is equal to, let's see, 50 divided by 5. 50 divided by 5. And y bar is equal to, it's 20, 33, 42, 50, that's correct. And y bar is equal to 83 divided by 5. 83, y bar is equal to 83 divided by 5. This is 16.6. That's 10, this is 16.6. Okay? And then B1 would be 171 divided by 190. This is 0.9. And then B0 is equal to y bar, which is 16.6, minus 0.9 times x bar, which is 10. So B sub 0 would be 7.6. 7.6. Now our line regression equation would be 7.6 plus 0.9 times x. All right. Okay, next, least square method or least square criterion. Least square method or least square criterion. On slide number 10, which I think this should be probably slide number 16 or 17, but that's okay. There is a concept called least square method. Let's see what it is that you're talking about. With least square method. In order to calculate the coefficient of correlation, coefficient of correlation shows how strong the relationship is. And also in order to find the correlation of determination, there is a method called least square criterion or least square method. In this method, we are calculating the difference between y variable and y bar, and also y variable and y hat. The first formula of the least square method is as such: sigma of yi minus y hat squared. Okay? This has been used in order to develop another formula which leads us to calculate This is leading us to calculate sum of square total equal to sum of the square due to regression plus sum of the square due to error. Sum of the square total equal to sum of the square due to regression plus sum of the square due to error. This SST is actually using that method of least square method. The SST is actually sigma of yi minus y bar square equal to sigma of y hat minus y bar square plus SSE, which is sigma of yi minus y hat square. This is, again, sum of square total equal to sum of square due to regression plus sum of square due to error. Excuse me, guys. All these formulas are listed on that page, this page that I have it uploaded on the Beachboard for you guys. All right, on this page. Now we use these in order to find the coefficient of determination and coefficient of correlation. And then later on, you see that we're going to somehow use it indirectly in order to test for the slope. What does it mean, testing for a slope? Slope means if there is any relationship between the two. If the value of the slope, that means B1, is 0, there is no relationship. If the value of the slope, that's B1, is positive, then there is a positive relationship. If it's negative, then there is a negative relationship. But for now, using it for coefficient of determination, that's equal to lowercase r squared SSR divided by SST, and then coefficient of correlation, that's equal to r, lowercase r sub xy, which is equal to square root of r squared. All right, so we use this method that leads us to this formula in order to find coefficient of determination and coefficient of correlation. Again, what is coefficient of determination? Coefficient of determination is used to show what percentage of the actual value of y can be estimated or determined by any given value of x. Or another way of saying this, for any given value of x, what percentage of the actual value of y can be estimated or determined? And then for coefficient of correlation, It only shows how strong the relationship is. And it is measured between 0 and +1 and 0 and -1. 0 +1 for positive relationship, 0 -1 for negative relationship. Now let's see, I think we're gonna do a problem on, if you guys go through the slides, they are doing that for that example. They are calculating the coefficient of determination and coefficient of correlation for that example that they were using. Now let's do problem number 15. Problem number 15. For 11th edition users, page 580. For 12th edition users, page 619. And for 13th edition users, page 620. Problem number 15. Problem number 15 is using the data from problem number 1. These are the data from problem number 1. Okay. The estimated regression equation for these data is part A. No, I'm sorry. The estimated regression, so they given us the equation. If you guys remember, the equation was 0.2, I think 0.2, yeah, 0.2 plus 2.6x. This is given. For part A, compute SSE, SST, and SSR. So using those equations that I gave you. So to find SSE, yi minus y bar, SSE is equal to yi minus y hat squared. Sigma of yi minus y hat squared. This is for SSE. Now, first, we need to find y hat, of course. To find y hat, we have to do yi, these are yi minus y hat. First we have to find y hat. So y hat is equal to 2.2 plus 2.6. X is equal to 1. Okay, y hat would be 2.8. Okay. So another y hat, 0.2 plus 2.6 times 2. It's equal to 5.2 plus 0.2, that's 5.4. We do everything for the other ones the same. When x is equal to 3, when x is equal to 4, when x is equal to 5. So that would be, I think I have those values. This is 5.4. The other one is 8. 3 times 2.6. That is 7.8 plus 0.2, that's 8. And then when it's equal to 4, it is 10.6. And when it's equal to, when it's equal to, when it's equal to 5, then it is 13.6. So 0.2 plus 2.6, just do the same thing for this one. Okay, so those are our y hat. Now we go ahead and do, these are y hat. Now we do yi, 3 minus, 7 minus, 5 minus, 11 minus this, and 14 minus that. So yi minus y hat. I'm going to write down the answer in here. Yi minus y hat. I have 0.04, 0.02, sorry, 0.2, and then 1.6, -3, and then 0.4, and this is 13.2, and this is 0.8. Okay. Now we have to square this, then add them all up. Yi minus y hat squared, 0.04, 2.56, I think. This is 9, -3, that's 9. This is 0.16, and this is 0.64. We add them all up, sigma 12.4. So our SSE would be 12.4. So I'm going to do SSE 12.4. SSE 12.4. I should have kept those y hats, but that's okay. So next, let's go ahead and find SST. So SST is equal to, put into the formula, sigma of yi minus y bar. Those of you who remember, y bar is equal to 8. So yi minus y bar, 3, 7, 5, 11, and 14, minus 8, minus 8, minus 8, 8 minus 8, negative 5. That should be square. Negative 1, negative 3, 3, and 6. So yi minus y bar square, 25, 1, 9, 9, 36. No, you apply the sigma, that's equal to 80. Okay? So SST is equal to 80. Equal to 80. And then we have the formula. SST is equal to SSE plus SST, or SST plus, I'm sorry, SSR. So SST is 80, SSE is 12.4, plus SSR. So solving for SSR, it comes out to be equal to 15, 67, that's 0.6. So that's 80 minus 12.4, that's 67.6. That's our SSR. Now, don't panic. On the final exam, when it comes to these kind of questions, I do give you the values of SSE, SST, and SSR. So you don't have to spend so much time doing those calculations. So this is problem number 15. All right, let's see. Now, the last and the most important part of the chapter 14, this is testing for significance. Now, let's see what that means. We should be able to use line regression formula and least square method to calculate the coefficient of correlation, coefficient of determination. Oh, by the way, for that problem, let's see, we had for problem number 15, let's see, if we wanted to calculate the correlation of determination, R squared is equal to SSR divided by SST. SSR, I think it was 67.6 divided by 80. So if you guys go in and do this calculation, yes, SSR 67.6 divided by 80. This gives us the, let's see, like about 0.8 something. Say 0.82. I don't have the calculator handy here, so approximately 0.80 something. And then this is coefficient of determination for coefficient of correlation, square root of r squared. So square root of 0.82 or 0.83 or 85, whatever that is. That's going to be what, 0.9? So Rx sub xy approximately is going to be 0.9. So that tells you that this is a very strong positive relationship between the two variables. Now, these are not part of the problem in the book, but we're going to do one problem again. I just added these to the problem, for you to see how we are using those values in order to find those SSC, SSR, SSTs, in order to find the value of coefficient of determination and coefficient of correlation. And this is how we interpret it. If it is correct, if it's 0.82, like 84, 85, whatever percentage, we say that for any given value of x, any given value of x determines 82% of the actual value of y. This is called coefficient of determination. And this, of course, is showing how strong the relationship is. I think I'm going to stop at this point, and the rest of it I'm going to cover in the next video. And if you guys have any question, please email me regarding these videos. Thank you.